guess my first question to the panel here would be how fast has ZK been evolving, right, from research papers to actual implementations, and how quickly it is happening? Because let's say a researcher comes up with a paper, right, in no less than a few weeks, it's already being used in action. So if the panel could take this up.
So the way I would describe is the following. So 2011, Pinocchio was initially proposed, and then first of the schemes, no, it's not Pinocchio, 2013 is Pinocchio, right? The first of the things which is essentially converting the Fiat-Shramee transform that actually converts interactive zero knowledge to zero knowledge happened. So somebody figured out you could actually use a member tree to do interactive one and non-interactive one. And 2013 was the cache, and then by 2015, 2016 October for sure, because that's when I was reached out by some of the people to see if I could do a setup for a version of it, which has replaced the hash function that was existing with the SHA-256. In hindsight, when I think about it, it's a bit ridiculous, but that's what it does. So what literally has happened afterwards was like, there's a very long period of lull that was there from 1985 to like 2011 when census peak. And suddenly, there was an acceleration, a true acceleration. So there's this blog post that if you ever get bored and you want something to read and go back to sleep on, Eliban Sasson of Starkware actually wrote a piece, I think it's on A16C's blog post, the Cambrian evolution of zero knowledge proofs. So it has a good number of graphs, but think of it like, you going back to grad school. So there is this, description of things from the computational complexity perspective. Coming back to it, so what has actually happened? So there were three things that happened. Number one is, normally all cryptographic primitives take a while. I don't know if you were there for the panel that was happening here. Somebody asked me, I can't remember the person's name, the person was sat out there, and he asked me about test vectors and things like that, and I told him about the ZK proof 2019 and things of that sort. So what I'm saying is, normally whenever you come up with a cryptographic primitive, you have to do very rigorous testing. So just so that you all get a sense of it, I was just having a chat with Mark about, yes, so the place where we both went to grad school, they had two submissions, and this is in 2000, 2001. 2001 it was all fixed. But that's 25 years ago. That changed from BES to DAS to AES took a good while, right? So it's not a kind of thing that happens like this, right? So what literally happened with crypto, and this is the paradigm shift that really made this happen. Until crypto, if you had to ever create a crypto primitive and try to use it, you'd be called a snake oil artist straight up, no questions asked. The first thing that you'd be accused of is being a snake oil artist. In the world of crypto, the criteria for, let's think of it the other way around. If you're really cynical, you go, the set of people that are there that actually really understand crypto, cryptographers, are very tiny, okay? So what do? You anyway push it. So this goes back to another conversation we had yesterday about that, verification or audit of smart contracts. Amin was saying, he actually went through the whole source code for Gnosis Mondays, right? Same thing applies. So here what has happened is zero knowledge, there's been some improvements, and suddenly you had all these things coming in. There was very little validation, and there was a real massive push. So one of the schemes that's still being used the most is Growth 16. It probably has the largest amount of money behind it. And then Plonk came along, and then a Plonkish bunch of things came out. Then there was Sonic, and then there's this lookup mechanism came out, and that has come the most recent one. And everything that you could think about has been thrown at the ZK wall, as in you throw all the whatever. Given its Zu-grama, it's poo. You throw all the poo at the wall, and whatever that sticks is whatever it is. So this has been the paradigm that ZK has been for the last, I would say, since 2016, for the last 10 years. That's my 2 cents.
Thank
Thanks a lot for a very complete picture of how it went. My experience has been rather focused in a specific area related with implementation of verification. And so initially this was just like a concept, and like people did not quite know they could do the pair. So my experience revolves around pairings and Prot 16. So after like Miller said that actually you can compute pairings, this was in like 1985 or something like that. And yeah, thank you. So yeah, after that people started to think of ways you could actually do the pairings, and then we had like Tate pairing. We had a bunch of pairings, but I think like Tate was first one which was sort of computable. Then we had 8 pairing, which was 8 and optimal 8, which are actually in use right now. Then like NARIC came up with his first like nice pairing computation in 2010 or something like that, maybe 2009 or 2010. And from there it became sort of like a war, like who can do the fastest pairing between NARIC, Bischoff, et al. And Arana. So NARIC said that we can use the tower approach, and we can use this optimal 8, which is like fast, and I can do it in like this much time. And then Bischoff shows up and he says that, yeah, this is cool and all, but what you can do is actually you can, instead of trying these low-level functions just for your field, first field, like single field element, you can expand this and write precompiles for FQ2, which is a field extension of 2, and now you have much better performance. And then Arman says, oh yeah, that is nice, but you could do something even better.
Yeah, I was about to say, the thing that field Q2 is interesting in hardware. So if you want to really do hardware acceleration, that's like most amenable to that. So that really helps. So like if you have, so you have like 2 things that typically happen at the same time. One is mathematical speedup, other is the hardware speedup. So the mathematical speedup, when it happens, it really changes the whole game. But the hardware speedup is kind of a second order impact of Moore's law. Effectively, I'm sure everybody here knows Moore's law. If there is anybody who doesn't understand Moore's law, just show me a hand, I'll buy you coffee. Okay, there you go. Somebody missed the coffee. Could have just said that. You could have free coffee. No, not now. Too late. So what happens is, like, as computational, the improvement in hardware continues. We have a non-linear improvement in actually being able to do the compute, and that with the Q2, like field of 2 is essentially GF2 is essentially allowing you to do things much faster, even if there is no significant breakthrough. Right? So it's like if you have a significant breakthrough, think of it like there's always this curve going, and then suddenly it's like, then goes that way, then it goes. So that's typically not like this, like jumps.
Yeah.
Sorry, please continue.
Also, like these people sort of use their own custom curve, which actually I realized much later. They have this like BN curve, which is also 254 bits, but it's not BN254, which you might think. And like I was so, I implemented the whole thing, and it was taking much longer than what it was supposed to based on the paper. And then it turned out, yes, it is the BN curve. Yes, it is 254 bits, but it is not BN 254. So anyway, yeah, then Arana shows up.
Yeah, I was about to say, welcome to the world of curves. Everybody has a curve of their own. So like, some one of these guys wake up in the morning, and instead of having coffee, they might come up with a new curve. And each of them will have a different property. You can do certain mathematical operations in that curve for certain characteristics, and it wouldn't work for anything else, and that's kind of wrong. Like it's a good thing and a bad thing. So if you think about the curves that we have in Ethereum and other L1s, it's a trade-off, and that trade-off has actually set us where we are. So it goes back to this question: what happens when somebody comes with a curve?
So finally, Aranya can come now. It's second time he wasn't able to come. Yeah, anyway. So, yeah, he says that, okay, now, when you're multiplying two field elements and you are actually adding them right after, what you can do is instead of like reducing them, like you have to do everything in a modular thing. So instead of trying to reduce them after every multiplication, what you can do is let them be like your twice the size of the integer, and just add them first and then reduce them together. So when you do that, you lazy reduce basically. And then he has this very nice table at the end of his paper. He shows very nicely, like, it was taking these many operations before, but now it takes like these many operations, and I try to, I computed based on like my primitive CPU steps, and then I think, oh yes, it's gonna fight in a transaction. Because like I was trying to do it for StarkNet, and like Karaka has been at it for like over a year, and they were actually waiting for like a modular built-in. I decided to do it without one, so it was not very efficient. Yeah, then like this was all nice. Like Aranya's work was quite helpful. Then some people show up and they say like, actually, you can do a proof and then you can do a proof of the verification. So now you can have like recursion here and you can save a lot. And I'm sure there might have been many people, but the most prominent one that I personally love, this guy, his name is like Yusuf. He works at Consensus, and I chat with him when I work on NARK and stuff. And this guy says that when you're trying to do a verification inside of another circuit, essentially, what you can do is you don't really have as much of an expense on division, because division on CPU is very expensive, multiplication like at least like 100x cheaper. So everybody was trying to just do avoid division to add like 10 multiplications. So then Husni, yeah, it's his GitHub handle that I just say or kill Husni. So he does. He says that you don't need to do that. You can just use the old simpler one, and it is actually more efficient than this more complicated multiplication-based one. Yeah, and then finally we have the recent one, which actually made it possible for me to make true on my promise of fitting a pairing in a transaction. It's from Geometry. It was released last year in maybe May or June, something like that. And yeah, this one actually eliminates final exponentiation. It sort of makes it so that most of its stuff, like the squarings, can be shared with the Miller loop itself, and then you have.
So if you don't mind, can you walk us through like how the compute would be? Like, is it like a Python 50s kind of thing, or MSMs, something else? What would be the size support? Just giving an intuition to people, so if anybody's interested, they get an idea of what's happening.
Yeah, so with final exponentiation, the biggest challenge is this thing called exp by x, like, which is basically you're trying to do a huge exponentiation on a field extension of 12. So that's a very expensive operation. So we have to do it actually 3 times in the final exponentiation, because you do it once, then you do some more operations to make it suitable, then you do it again, and then again. So like what you're trying to do is basically raise it to the power of, I don't remember exactly, but so if you take something to power of like the field size, then it basically becomes like same as the how to describe this? It's more applicable to field extensions. So whenever you raise something to the power of the field size, it is the same as that number. And when you do it in a field extension, it becomes the same as the original identifier sort of. So you can have like different fields. You can have different FQ12s, but they all refer to the same element actually. And this is why you need final exponentiation to reduce everything to that base element. Yeah, so geometry said that.
Shramee, I guess going back to your previous point on recursive aggregation.
Oh yeah.
Yeah, I think we've seen that quite a bit with rollups. We've got a handful of ZK rollups live, and there was a time when the proof volume being submitted to Ethereum was increasing, but once recursive proof aggregation was implemented, the proof volume actually started going down quite a bit, even though rollups were generating proofs continuously, and that reduced a lot of I think verification costs as well.
Yes.
So it's already having quite a bit of an impact, and I guess Arman, if you could. Add in.
So coming to recursion, like as you told, like most of the rollups use this. So I guess the best paper that you can read about this is Pinocchio, how Polygon ZK VM uses it. So when they made the whole repository about star key and Pinocchio, so if you dig down a bit onto the blog or the research papers, you can see that all the transactions or the bunch of transactions, those are particularly proved using star key, which is a star-based paper or an implementation. And then this star-based implementations are again recursively proved inside a block-based kind of proof. So basically they batch up multiple kind of proofs together for multiple blocks, and then they post it in a single proof on-chain, right? And from that, like we got a lot of different rollups adapting that. There are Scroll, Typer, everyone who are building their own recursive tools as well. So like the next gen kind of privacy rollups, let it be Aztec L2 or Polygon Maiden, all of them are trying to do the same, but they have their own Maiden VM, or Aztec have their own Noah-based recursion things, where they are trying to do with Ultra Honk and all these things.
Right. And this is mostly about pieces of infrastructure. But let's say there's a private application, right? So let's say something like a dark pool. The dark pool would also have proof requests that it would send out to. Do you think applications would also forward their proof requests to prover networks where they could recursively be aggregated, or is it a different story over there?
I guess in the future, as we more get into the state machines-based ZK apps and all those things, proof recursion will be the best way to do so. And why I think like that is because as we make a lot of transactions on the state machines, how it generates a proof, it basically patches all of them and try to make it a single proof out of it, right? So I guess that's the best way to go. And even with the implementation that I'm trying to build with CuStack, we're doing the same thing. Like you post a lot of transactions to the ZK VM, and we try to recursively prove and do stuff with them.
Nice. And taking it forward on ZK VMs here, I guess how do you guys see ZK VMs impacting how developers build ZK applications?
Yeah, so ZK VMs have made it really easy for normal Rust devs to say to come on and build ZK-based applications out there. So the initial idea came out with Valida. A lot of guys out in the crypto market don't know about them, but the initial idea was laid up by the team of Risk0 and Valida. And then guys like SP1, Nexus, all of this came up, and they took ideas from all of these different things, also from software, and they tried to build this whole thing up where you can write a randomness code out there which has its own state and its own kind of actions, and we try to prove the same thing again and again using the ELF files. So also coming to that, like there are also ZK VMs like ZK Wasm. So they plan to onboard more developers into the ecosystem by giving options like JavaScript and Python to devs, so that they can write the same applications out there without knowing Rust, and they can make a Wasm compilation which can be proven around.
And I guess all of these devs, they don't even need to learn the core mathematics or anything related to ZK in depth to build those applications. But if you have anything to add on this,
yeah, I mean, it's a good thing and a bad thing. So I would go back in time, and if you were in the 2000s, we would describe anybody who called hack things. So it's this age of script kiddies. Script kiddies are the people that have actually managed to run a script and get into a machine, but don't know what's happening. So I think the age of the script kiddies for ZK is there. So that's also a good thing. Yes, there's more adoption. At the same time, the downside is like they don't understand what a constraint stands for, and your proof is as good as your constraints, right? Like, you need to design your proof so that your constraints meet your real world. If there's an inconsistency between the constraint and the real world and the constraint that you represent, your proof will still be valid and you won't be getting a real representation. So this is one of the challenges we have. I call it the brain proof gap.
So coming to that, right, Anish Mohammed recently posted a huge debate around, like, she basically posted that instead of using ZK VMs to prove EVM blocks, rather it makes easy to make ZK VM compatible things, either with ZK or any other SNARK-based systems. Like, instead of using ZK VMs, which gives you a lot of flexibility, but it also increases the cycles and a lot of computation overhead to you. So she suggested we can, for a specific system like ZK VMs, which we definitely have a lot of volume coming in, so it makes much more sense to have specific proof systems built with low-level engines out there, and then we can scale it back to ZK VMs. So I guess the future is a mix of both the things. We'll backing ZK VMs, but also for some of the specialized applications, we will use like more DSLs and all those things to be constraints.
Right. I guess coming to DSLs, I think we have Noir out there. Then there's Cairo and a couple of others. How do you think they fare against each other? To spice things up.
I am primarily a Cairo dev, but I love Noir just as much. So I hate Circle.
Same too.
I probably will have to admit that most of my team is on the other side here, a Circle bunch. And just to be very clear, so some of the guys who work within our team, they wrote the original catches in C++. So it is like the fashion, right? Like if you had phones, the early phones were the phones which, big buttons, you have charge it works for, pretty 2 weeks, you throw it, it still works. Now you have the iPhone, you have half a day, very fancy, and you throw it once, you're done. You can't do anything after that. So like, horses for courses, there are lots of things makes things easier. Yes, Zugrama is not the most friendly of all things. It has been around the longest. It does have bugs. I'm not saying it doesn't have bugs. We found some bugs over reordering. So, my thinking would be like insecurity, low security. You can always imagine there are low probability events. Okay, so it's like imagine you say that if you hit the door 1,000,000 times, 1 in a million, you hit some part of the body that part of the body will be not functional. You can choose what part of the body that is, right? So you consistently bang yourself against the wall. You could be 100% assured that will happen, right? So this is security. So when you have tools that are being used more and more, the more of the attack surface has been explored, and you could have higher levels of assurance. Yes, there is always been this trade-off between usability and security. And I would even go as far as to say usability and, usability in that sense. Usability for the humans that use it, and usability for the humans who are called the developers, or I would say the prompt engineers who now are the interface between the machines and the humans to create the code. So, my 2 cents.
Yeah, while I do hate Circom, but for people who write Circom, I just have for them respect.
Really early the devs throughout the whole ZK thing that we are seeing, like when all the OG devs out there, we are seeing like they have written most of the circuits in Circom. So, yeah.
And the thing you need to recognize is like if you go back in time, you look at the compilers, right? Day one, there is one compiler. Every other compiler that comes in, or every other language that comes in, is written the first compiler, right? So, and this is the funniest bit that most people seem to not recognize. The bugs that you actually have the first compiler would actually be propagated to all the compilers that follow. because you use most likely the same mechanism to access everything you want to access by writing a new compiler. The same applies to the Zugrama story. So, if you had to write a new thing and you want to get it through the pipeline, you probably end up using one of these toolings that's available for you from something else. It's not one-to-one map, so just to be clear, the Zugrama doesn't do sort of things. So you can't think of it like. So going back in time in the 1970s, you had C as a compiler. A lot of other languages just came in. So if you think about other languages, you will find that those languages were written in C. It's unlikely somebody will write everything in assembly. Yes, there are people. There used to be people who are like, who you just give them a hex dump and they could just write assembly code, right? Those people are now very few and far between. So, C, every other language uses C as a compiler to create a new compiler. Kind of the same kind of construct, in my mind, has actually happened with Zugrama and all the other tooling that came after. So prior to Zugrama, there were a bunch of people who actually wrote C++, C++ catches. So Zugrama kind of inherited that. So if you were to think any of those real functional problems that exist in C, don't be surprised. Whatever tooling in ZK still has it.
And I guess one last question for the panel here. As ZK has been advancing so rapidly, to what extent do you think we could see them be used in applications where it makes sense? Because the cost of generating and maybe verifying proofs has been reducing drastically with newer proof systems, shorter proof sizes, we have client-side proving, right? And I guess with also ZK TLS around, we do have a lot of ZK related things, but there might be a line where ZK is actually useful versus, let's say, another piece of cryptography or technology would instead be more efficient for the cause.
So I'll be the cynical guy. I've been in ZK I have been interested in ZK for a long while, probably less than the gentleman who's sleeping right now. Well, Mark. So he actually did his PhD using ZK to provide proofs for detecting collusions in a PC, right? So not that much, but less than that, but long enough. So the thing that happens is when something gets fancy, just think about LLMs right now, right? Like you ask it, oh, now it's agents. So you ask anybody, here's the problem, what's your answer? It's an agent. So for a period in time, you have a question. It's like if you see anything, you have a hammer, it looks like an agent. So this was ZK for a long period of time. But a lot of the times you really don't need ZK. I mean, you can achieve the same set of results with a bunch of other things. There are, again, there's this question about decentralization versus centralization. Sometimes a combination of DEs plus NVCs or something like that might get you all the results that you require. But again, this is a question of your trust model, your security margin, how much are you willing to pay for your throughput, and any other constraints that's being put onto you by your ecosystem.
For the very first thing, I'll say, as Anish showed, a lot of people out there or companies out there just using the word ZK to it without the need of it. I've seen circuits, they just check out random hashing and they're like, we are using ZK. That doesn't make any sense. So I guess there needs to be proper implementations of ZK-based ideas. There are multiple teams working on DeFi identities and a lot of different stuff. So I guess with the more usability thing, the ZK VMs and the proof cutting with the proof markets and SNARKs and all these things coming up, it is becoming easy, and we are very near to scale ZK to some real life applications. But yeah, we need some really good devs to ideate some things which really it needs ZK and try to build that up. Yeah.
All right. And do we have any questions from the audience? Okay, all right then.
To what Anish just mentioned, that there would be many ways or workarounds that produce a viable substitute for it, what ways are there and when they are indicated, and when can I see that the ZK mechanism that some product wants to build in is actually just performance and really needed?
Okay, I'm going to give you a very obvious example, right? The obvious example is ZK rollups in L2s, right? There is no way in the current ZK mechanisms, a set of all ZK mechanisms, that you would be cost compatible or throughput compatible with an optimistic one. Because what you require is an exit insurance in that sense. You really don't require cryptographic proof. You're going in, you have proof. Going out, you don't have a proof. But you take an optimistic view in that sense, like in a week's time you will resolve it. If you implement some sort of an insurance mechanism, there is no way that a ZK mechanism can compete cryptoeconomically with that, right? So that's one. Another example I'd say is like, you have all this tooling that's available for most things. You can get, some sort of an attestation with just hash functions. You always have public crypto that's available for you. If you want certain edge cases, you have TEs available for you. So if you have devices where your code base is running, and that's TEs available, it's free. Meaning what I'm saying is like, there's a cost that's associated with having ZK. So if you have ZK on an L1 or on L2, Ethereum, 300K gas, right? So even in an L2, a significant amount of cost. And it's not just the cost of gas in that sense, it's the cost of the time it takes and the hardware it requires. It's just so that you understand what it really means, because this might sound very abstract. Think of Filecoin. They have 1 million constraints. They have grown 16. Guess how many hours it takes on an average? 6 hours to 12 hours. That's sealing your data, right? So this is why I say, like, there are forces for courses. You can actually get some of the things done. You're pretty sure you're not sitting on a server. A server is most likely, when I say TEs, everybody might say, oh, what the hell? Windows now almost requires you, Windows 11 almost requires you to have a TE to deploy. As in, you want to have a machine, your machine has a TE inside. Hey, it's free. Now you paid for it anyway, that's what I would say, right? It's like when you're staying here, breakfast is free. Whether you want to wake up and go have breakfast is a question you want to have. If you're really hungry, that might be something you want to do. That's the way I think about ZK.
Just as a follow-up, that addresses ZK in blockchain. Would you discard ZK outside of blockchain, let's say for also offline applications, as something separate to handle?
Yeah, so the way I would describe it is like the ZK in an offline, you have much less constraints, okay? So when you talk about ZK on top of any L1s, L2s, there are like a couple of things that you need to recognize. One, the L1 typically has a bunch of curves that kind of constrain what kind of mechanisms you can have. Number two is if it's an EVM one, there's a gas cost, and that's a significant amount. Number three is the storage cost of the proof, that's the size of the proof in that sense, right? So all of this, plus assuming decentralization, that implies motion, right? Whereas in a normal situation, you don't have these constraints. You can just decide, okay, you're not constrained by the L1 to choose a curve. Like he was talking about various curves and things like that. A lot of the advantages you have there doesn't come to an L1 because the L1, if you really want to change anything in an L1, this must be an easy thing to do. You just want to scratch your nose, right? That's a very easy thing to do. You have to have a chain of the people and you scratch everybody's nose. And at the end of the circle, they scratch the nose for you. That's typically how things work in an L1. So in a real world, you have far less of a constraint. You are in control of your hardware. You might be able to do a lot of the things very efficiently. And it is very possible that ZK could actually give you the kind of properties like in privacy, assuming you're interested in that. This is a constraint we have. Like, not everybody is interested in privacy. And there are a whole bunch of us who really believe in it, and society really believes, well, no, I wouldn't say that. Society really is kind of dependent on the existence of the constraints of privacy, right? If privacy no longer exists tomorrow, we might have a whole bunch of societal challenges. I don't want to go into it right now. Use your imagination, right? Think of all the different things. I know Amin gave you a picture, but that is nothing. That is a novel function. There are other functions that are optional. Those will be more interesting, and variants of that will make it even more interesting. And everything else you do becomes more and more interesting, right? So, depending on where you are on the spectrum of society, where you value privacy, then you might be able to choose, do some trade-offs. Say, instead of me buying a laptop that's worth $1,000, I'm willing to pay $1,100, where I have $100 worth of extra hardware that accelerates ZK. And everything I do on my machine now will actually use ZK, because I have a ZK hardware accelerators built in. Right? That's very possible.
And my last upcoming question for that, and would it be possible to use the other cheaper on-chain methods like hash functions or like you name it, in combination with the rather centralized or unrestrained ZK of hardware or offline basis?
Yeah, yes, absolutely you can. It's a question of how you build your trust. The trust model is a question. Where do you bootstrap your trust from? If you bootstrap the trust from all the hardware that's outside, absolutely. You could literally have all the, in one sense of speaking, the so-called proof markets is kind of this, not really this, kind of this. Web3 is never this or that. You ask them if it's tea or coffee, in the morning it will be tea, and in the evening it will be coffee. And in the middle it will be half tea, half coffee, right? So the way I'm saying this is like, you can think of this as oracles, standing towards the L1, L2, whatever it is. And the oracles could actually do your stuff for you. So you could actually have this heavy lifting done by these oracles, and these oracles could actually provide you the true step. For you, on chain is a boolean, which is like a 0 or a 1, yes or no, right? You can do whatever you want. So yes, you could do all this magic. But again, this goes back to the question of like, what do you really value? Do you value decentralization? Do you value 10 machines which has, I would say, 128 gig RAM plus this, that, GPU, okay? I'm not pointing fingers at any other ones of any kind, or storage solutions of any kind. If you recognize any of them, you know who I'm talking about, okay? So, that's how this works. Horses for courses. If you really do a decentralized one, you have a certain set of characteristics, and that's the characteristics you have if you ever want to do some proof of work or some ZK stuff. If you proof of stake, it completely changes. So, you need to figure out where you want to be, and then you can use the tools that's available.
Okay. Oh, question.
This morning we had SNARKs, we had SNARK presentations. Maybe you can do a bit of like consolidated comments, like comparing where they are, what are the kind of camps that use one or the other, or what's their strengths now, where is the future, how you see it, what are the scenarios?
Yeah, I think I will try to do one bit of it.
Maybe I can add from my side that you can also answer that's like related to this question. It's a bit provocative question from my side. Does it aim to bring new people on chain, this ZK technology, or it's purely work for esoteric developers, cypherpunks, who is on chain already? Just from that perspective, and what will be the use cases in future maybe for ZK technology?
I'm going to ask the reverse question. Do you think light bulbs allow humans to have more productivity?
One more time, didn't get this.
Did light bulbs you think light bulbs allow humans to have more productivity?
Yes.
Okay. In general, technology, loosely speaking, the way I see it is technology. You should always think of this as a technology that actually has unique properties. A whole bunch of things we couldn't do before, you can do with ZK. The same way we didn't have the ability to work in the night. If you actually had, if you were in the Middle Ages, by like 40, you could no longer read, write in daylight. I mean, like after daylight, right? That's very restrictive. Just having the fact that you have lights that give you the ability to work much longer, right? Made a significant improvement in productivity in that sense. The same way, what I would say about ZK is like ZK has some, in my mind, at least magical properties, right? I could prove to you things without ever showing you what it is. You could be assured, as long as you believe in math, that what I said to you is true. And I could be assured that as long as I tell you the truth, that you be convinced. This is absolutely magical. Can you think of anything else that will give you this assurance, other than God or anybody else? Don't bring God into this argument, but like any mathematical one. I'm happy to take a challenge, right? That's the thing. So it is a real breakthrough technology. How we implement it is questionable, right? Like with all things. You know, you could use it to do like, you put bulbs to light a place up, sometimes you use it as a decoration. Do you think decoration really adds value? It's an aesthetic question. You know, you can't actually give an answer to that one. I am not well informed to give you an answer on that one, right? The aesthetics of it. Definitely I can give you an opinion on light and definitely improving it. We can have a chat, we can see each other, right? Like, that definitely is a thing. So that's first thing. Going back to Asani's question, Asani, I wasn't thinking you would throw us under the bus, but here you go. I'll give you like a loose kind of thing. So I've deployed both on SNARKs and SNARKs. The thing I would say is like, there is no one answer, right? It depends, is the first thing one needs to understand. And one of the things that has also happened is like, so there are two commitment mechanisms. One is FRI and another one is ZKD. So kind of what has happened is SNARK, where I just described anything that's FRI, that's SNARK. It's like if, you know, Alexander Fleming just turned up and said, you know, everything is antibiotic and I have the company, right? Just imagine that way. So that's kind of what happened. So, you know, kind of that happened. Good things about it is like you don't need a setup. Because of FRI, you can just, if you have a collision resistant hash function, your security properties are met. And, you know, other trade-offs exist. If you look at the snarky side of things, the security is pretty much based on pairing. So if the Chinese tomorrow publish just like they did to DeepSeek, you know what, guys? We actually have like a QC that could easily do 2,000 bits. We will all have big heartaches, right? That's one problem. And the other problem you will actually have is you need to run a setup process. So there are universal setups and other setups per circuit in that sense. If you are thinking of growth 16, you will actually have to do setup per circuit in that sense. Longish ones you just do a universal setup and you can actually do the thing. Right? So this is, oh shit, oh sorry, my battery ran out. Not my battery, my microphone's battery. So the thing I was about to say was like, you know, in that sense, SNARKs definitely have some advantage, right? Which is essentially, A, you don't need a setup. B, you know, you have quantum resistance. At the same time, there exist these problems about the size and throughput and things of that sort. So it's very much depends on what you want. And the combination of it, which is like Halo 2 and things like that was being discussed. So you use different things. You use SNARKs to create the proof and a SNARK to roll it out. Okay, so you can have. But then you might ask me, well, you know, you'll have problems with both. Yes. You can have the downside of both, and you can have the upside of both.
And what currently, how you evaluate the strengths of the two communities, and in terms of like any immediate use cases, who's better suited, who has like currently have?
There's a SNARK person there. Let him respond, and then I'll.
Yeah, I had something to add to your previous question. Like, it's not like, it's how, so if you had some use case where you need individual user to provide a proof of something rather small, so let's say you're making a transaction and like, you want to say that I transferred this with a set of rules and this is transferred to someone, and that someone is let's say like not a criminal or whatever, you know. So that is a rather small thing. So whenever you want to prove something rather atomic, you would want to use something like growth 16. You would want to use growth 16. It's a SNARK. That's what I've kind of worked on as well. And if you have something rather complex with a bunch of like state machine stuff, and it's got like a lot of computation, and like you don't have a good like a good bound, like your computation is not well bound, then you would want to use SNARKs, because when your computation rises a lot, SNARK, like pairing-based SNARKs specifically is what I'm talking about. You have a hard limit and you cannot cross it. If you cross it, then it doesn't really work. I don't exactly know why, but there's like a hard limit on constraints like that you can have and practically compute them.
So I'm going to say something very simple. So for those of you who are working with stop where don't tell Yuri he left now, but don't tell Yuri I said this, but the security margin for stocks are 80 bits. So do anything that you want to do where you are happy with having security less than 80 bits.
You could do it twice and it's 160 bits.
Yeah, well, you know, that's like you telling me use dash, you'd be fine, use triple dash.
Sorry, can you repeat that?
Dash, yes, I talked about that first, the first day, right? So I kind of describe, it has a 56-bit security. You can actually, tie them up together to do 168, but there are very interesting attacks. You can attack from both sides and things like that, and that is also possible for SNARKs. So please don't ever take, somebody said, do it twice, doesn't work that well. A lot of the cryptography is when you do it twice, it doesn't really give you the security that you think it's going to get. You could attack from both sides because there's a gap between the two and you're opening it up. So somebody could actually understand what you pass from the first to the second. And wherever, when that happens, unless you're doing some magical stuff, your total security might be less than what you were expecting. You actually have Mark over there, he'll be very happy to hand it to you. What happened to doing this kind of stuff for primitive primitives? It's a good lesson to be learned. Like, A, lying to people is not good. B, saying things that, you can do this. While good, is not really understood. So lessons learned from previous instances is like, if you just do this chaining, doesn't always, like if you use dash twice, okay, 56 plus 56, you're not getting 112.
The thing is that I'm not very aware of the protocol or the system that you're talking about, but in SNARKs, the way you could submit a false proof is when you actually tweak something and then you basically hope that the verifier will not ask you something related with that. And if you probabilistically do it twice, then the probability of having that found out becomes double. So,
you only need to do it once. So in the world of layer ones, your cryptographic security margin doesn't say twice. You only say once. Consensus, once. You don't get twice. You drain everything once.
Yeah, but it's not like you don't have to do it in the system. It's just arbitrary code that you run. You can run any arbitrary code any arbitrary number of times.
No, what I'm saying to you is like, when you have a security margin, your security margin is your one-shot doorstop, okay? Right. So if you have something that's worth more than the price of something to the power 80 in that sense, you could have that one shot being taken and we'll go through. Once it's done, then there's no point in second iteration of that, right? Because it's not going to happen because everything has been emptied out. You no longer have anything on your chain. If you're a proof of stake thing that your stake there is zero next round, right? Because they emptied it out. Your stake is zero. Nobody's taking against it. Does that make sense to you?
Doesn't make sense to have it twice. Just having it once.
Yeah, there's one more thing you could do, which is field extension.
That's doubtful.
But it's okay, we can have this conversation further. Yeah. I mean, so I have a reasonable understanding of it because I wouldn't say, I understand it as much as I would like. So I wrote my thesis on attacks on elliptic curves. So I'm very familiar with curves and attacks. Yes, you can do extensions. Extensions can go both ways. You can go right way and you can go wrong way. A wrong way might hurt your parts of anatomy you don't want to describe in public.
True. Yeah, you have to do it right way, of course.
Alright, then I think we'll wrap up with this now. Thanks everyone for attending. And I think on Thursday we have Akshaya covering post-quantum cryptography. See you guys tomorrow.
So, just to let you know, we've had some very technical conversations, and we haven't offered any office hours. So, if you both want to offer office hours or Yusuf to an office, you probably can find them and ask questions. I just wanted to offer it to everybody, like, you know, because the conversation was between us, you probably want to point it at them, so, you know, you should be able to get off his ass. Even though Yusuf says no, he wrote a research article on privacy rules. So he's as guilty as the guy who wrote it. So he's not escaping.
All right. Thanks, everyone. See you tomorrow.